Hello everyone, and we are back with chapter 18, and we are finishing up with solar energy, wind energy, and how hydrogen can be used for energy. And these are all examples of renewable energy alternatives. So of course that's going to take us all week to get through. So we're going to start our Monday and Tuesday lecture with chapter 18.3, which is solar and wind energy. Everyone should be familiar by now or have seen it in your neighborhood. People putting solar panels up on their homes. It's become pretty popular. And as of the publication of your textbook, at least, it says here that one day the Earth receives enough energy from the sun to meet human energy needs for 25 years, if it could be all harnessed. But of course, that's not practical. You can't capture all of the energy, radiant energy released by the sun. It would be wonderful if we could. It would be a wonderful source. So why aren't there more solar panels, and why aren't more people using solar energy? We're going to kind of get into the nitty-gritty of that as we move through the chapter. But we want to look at our guiding question first to get us started, and that's how can we rely on the sun and wind for power? And that's what we're going to be talking about today, Monday, and tomorrow on Tuesday. So by the end of the 2 days, we should be able to describe techniques for using solar energy to heat buildings and generate electricity. We should be able to analyze the benefits and cost of solar energy, and we should be able to explain how wind energy can be used to produce electricity. And then lastly, we need to be able to analyze the benefits and cost of wind energy. Before we get started, of course, we want to start in with vocabulary, just getting used to the terminology we're going to be using in the chapter. So we are going to be looking at passive solar heating, active solar heating, flat plate solar collector, photovoltaic or PV cell, concentrating solar energy, or solar power, CSP, wind turbine, and a wind farm. So go ahead and turn in your workbook and complete the chapter vocabulary for 18.3. And you can go ahead and pause the video here if you want to copy the vocab from the lecture. And just continue whenever you're ready. Alright, so we're going to talk real quick about this gentleman named William Kankwamba. And this young gentleman, he really loved to read. When he was 14 years old, he needed electricity to power a light bulb so that he could read after sunset. So he and his family actually lived in a village in Malawi, which is a developing nation in Africa. And few people in the rural Malawi have electricity. In the nearby library, William found an old science textbook that described how wind energy could be used to generate electricity. So he decided to build a windmill that would do this. He constructed a slender wooden tower, and on top of it he placed a generator. He put together using plastic pipe, bicycle parts, and a few other things he found in the trash piles. His mother thought he was crazy until one day he connected a light bulb to the generator. As the windmill's blades began to spin, light flickered in the bulb. Since that day, William has built other windmills that power light bulbs and radios and charge cell phones even. Electricity from the windmills even pump water for people in his village. The wind energy that can run an electric generator ultimately comes from the sun. But the sun heats different parts of the earth unequally, and this unequal heating creates air currents. Both the sun and the wind provide energy that can be put to use. So we're going to talk about how we can actually harness these different types of energies. And first we're going to be looking at harnessing solar energy. And there's two main ways, which is going to be put into two different categories: passive solar heating and active solar heating. So the sun provides energy for almost all life processes on Earth. From the reproduction of tiny bacteria to the opening of flower buds, every day Earth receives a huge amount of energy from the sun. If we could harness one day's energy, it would power human consumption for possibly up to 25 years. We may someday be able to use sunlight to meet many of our energy needs. However, we are still developing the technologies to do this. When we use the sunlight directly as a source of energy, without involving mechanical or electrical devices, we are using passive solar energy collection. This is the most common way that we harness solar energy. In contrast, active solar energy collection uses technology to focus, move, and store solar energy. And we're going to look at a figure later on that's going to show us a combination of both passive and active energy, solar energy collection. But let's first take a little bit closer look at passive solar heating. But first, we're going to look at the image on our screen, which is a greenhouse. And this is an example of passive solar heating. So greenhouses, thick window drapes, and the fact that it's south-facing windows are considered passive solar energy devices or designs. So passive solar heating. We use passive solar heating to heat homes and buildings. Passive solar heating involves designing a building to collect, store, and distribute the sun's energy naturally. Greenhouses, like we just saw in the image on the last screen, were designed to do this. Houses that are designed to use solar heating often have windows that face the south and east to capture the sunlight in the winter. In that case, you would want to cover the window shades at night when it was cold to help keep the heat inside the home. Features such as these work to conserve energy and save energy costs. So just taking a look at the image on your screen, we can see that we have the south or southeast facing windows. Okay, they are facing the equator in this image. They have a well-insulated roof and windows. They have flooring and a design so that when the sun radiant heat comes in, it will reflect off of these other surfaces and it will help to warm the area. We want to reduce the amount of openings on the non-equator facing wall because you would end up losing too much heat. So you want to keep that heat trapped in. Another thing that you can consider is the landscaping. So here we have some trees shading the area, so that can play a role in passive heating or cooling of a building. Let's look a little bit deeper and dive deeper into the passive solar energy. So I'm actually going to refer to an article called Solar Energy, which was written by Ian De La Roca just back in September of last year. And so in that article, they go through and actually state that passive solar heating is one of the best investments you can make when buying or building a new home. Passive solar heating systems save money, and studies that they referenced said that savings for a home that uses gas can be from $150 to $380 per year, and similarly, a home that uses oil for heating can expect to save about $210 to $520 per year on heating costs. So it is important to note that passive solar is something that needs to be considered when you're actually buying a new home, or you're building or designing a new home or building from scratch. It's not for installing in your current home. So to install a passive solar heating system in your existing home, it would require you to completely demolish your home's interior, reposition windows, add insulation or roof overhangs, and a lot more. So scratch that option off the table. So that's why people with existing homes use active solar heating, like putting solar panels on their roofs. All right, passive solar heating and passive solar cooling. So we've been talking about solar heating, but does that mean that it doesn't work for cooling at home? And no, that's not. Passive solar heating is one of just two design approaches under the umbrella of passive solar design. So that would include heating and cooling. The other approach under passive solar design is passive solar cooling, which focuses on dissipating heat or getting rid of heat inside of the home when it becomes too hot. So that would be more useful for areas that are tropical or much warmer, maybe Arizona or even in Florida, for example. Passive solar cooling is just the other side of the coin, and when well done, can also save you bundles on your home cooling costs. So, according to this journalist, what is the future of passive solar heating? And it says here, passive solar heating has been around for decades, and recent design improvements have led to better efficiency at each step of the process. So why don't most Americans own a home that uses passive solar heating? And so first of all, we have to think back to the fact that it's part of the initial design of the building. So that's one downside. A lot of buildings or neighborhoods are already built, they're designed, and this was just not taken into account when during the initial build. So we can't really go back and retake into consideration the lay of the property, where the windows are facing, how we design certain rooms or whatnot. So we have to move on to other options in that case. Another problem is, just like before, 10, 20, 15, 30 years ago or longer, when these homes in your neighborhood were designed and built, people hadn't heard of passive solar heating or cooling. So it just wasn't very popular, and that means it wasn't very practical. You're not going to see a lot of people implementing it. Passive solar heating leads to the reduction of greenhouse gas emissions, and it saves a lot of time and energy, but it hasn't become mainstream the way natural gas heating or rooftop solar panels have, and hopefully that will change soon. But again, most of these buildings that we're retrofitting weren't designed this way initially, so we don't really have any other option but to use these secondary methods or techniques. As we become more environmentally friendly and as we design buildings in the future, of course we're going to apply the knowledge that we've gained, and hopefully we will be building future buildings a little bit more environmentally conscious. All right, next, active solar heating. So of course this is going to be active, meaning that there's effort being put into it, or energy being consumed when we do this. So it's going to use technology such as solar panels to capture and store and then distribute the sun's energy. So in our image here, we have the solar panels that we're accustomed to seeing by now. You can see it on a real home on the right, or on a cartoon version on the left. The sun hits those solar panels, and then that is actually wired to into an inverter, which then is able to convert the DC electricity into AC, and then that's able to be utilized by the appliances in your home. And your home takes in whatever electricity that it requires, and then if there is any additional electricity that your home did not actually consume, you're still hooked up to the grid, and that extra electricity can actually be credited back to you. So you can actually earn money from the electrical company, instead of your meter counting that you've used energy and then they bill you for the energy you used. If you have enough solar energy, your home uses less than it generates of electricity, then the meter will run backwards and you will actually get paid by the electrical company. I don't know if that is true of all areas, because solar panels are becoming more and more popular, so we would have to look into our specific local, look up on TECO.com for their specific policies. Oh. Don't want to move on quite yet. So an active solar heating system uses technology to collect, move, and store heat derived from the sun. One method of active solar heating uses devices called a flat plate solar collector, which is sometimes called solar panels. A flat plate solar collector generally consists of a black heat-absorbing metal plate in a flat box with a glass cover. Sunlight passes through the glass, heating the metal plate. A long tube passes through the collector. Fluid in the tube absorbs heat from the metal plate. A pumping system circulates the fluid, transferring heat throughout the building, and heated water can be pumped to tanks to store heat for later use. Flat plate solar collectors are usually installed on rooftops, and they can be used to heat both water and air inside of buildings. So how exactly does the flat plate solar collector work? Like we said, in the flat plate solar collector, as seen in this image, sunlight heats this metal plate, and then fluid is running through tubing within it. And that fluid absorbs heat from the metal plate, and then a pump is able to circulate the heated fluid through the building. So generating electricity with solar energy. Because passive and active solar heating methods supply heat to buildings, they can reduce the need for electricity and other forms of energy. However, neither passive nor active solar heating produces electricity. Two ways of using the sun's energy to generate electricity are photovoltaic cells and concentrating solar power. So the photovoltaic cells. In the photovoltaic cells, or PV cells, solar energy is converted directly into electricity. These PV cells contain two plates. The plates of a typical PV cell are made mainly of silicone. One of the plates is rich in electrons. When sunlight strikes this plate, it knocks some electrons loose. These electrons are attracted to the other plate. The flow of electrons from one plate to another creates an electric current. PV cells have many uses. You may be familiar with small PV cells that power your watch or your calculator. Some power plants use PV cells to generate electricity from a wide area. In addition, individual households and businesses can use PV cells to obtain all or part of the electricity they use. On top of the roofs of homes or other buildings, PV cells are arranged in panels or contained in special roofing tiles. Concentrating solar power. You probably think of a mirror as something you can just check your appearance before you go out, but mirrors can actually be used to generate electricity through concentrating of solar power. Concentrating solar power, or CSP, is a technology that uses mirrors to focus sunlight in order to generate electricity. In one kind of CSP, hundreds of mirrors are positioned in a large area surrounding a tall tower called a power tower, as seen in the image 14. The mirrors focus sunlight onto the receiver on top of the tower. The concentrated sun's rays heat a fluid in the receiver. The heated fluid is used to produce steam, and then the steam turns the blades of a turbine. That then powers a generator. Because this process uses steam, it is similar to the way a coal power plant produces electricity. However, the sun, not a coal fire, is the source of the heat that produces the steam. So now we're going to talk about benefits and cost of solar power. The sun will continue burning for thousands of years. Therefore, it is an inexhaustible energy source. In spite of this, solar energy contributes only a small part of today's energy production. However, solar energy worldwide has grown by 28% since the year 1971, a growth rate second only to that of wind power. So more specifically, let's discuss the benefits. Solar energy has many benefits besides its endless source. PV cells and other solar technologies use no fuel. They are quiet and safe. Solar technology does not release greenhouse gases, and it does not pollute the air or water. Solar devices require little maintenance, and an average unit can produce energy for 20 to 30 years. Homes, businesses, and isolated communities can use solar power to produce their own electricity. This production requires dependence on power plants. Solar power is especially attractive in developing nations because many of these nations have a lot of sun but few power plants. In the developed world, most PV systems are connected to a regional electric grid. In Germany, owners of houses with PV systems can sell their excess solar electricity to the local power company. And in many states in the U.S., consumers can lower their electricity bills if they supply some electricity to their local electric company. Finally, the development of solar power is creating many new jobs. But always with benefits there comes costs. So what are the costs? The manufacturing of solar energy devices creates some pollution. In addition, with the technology we now have, some regions are not sunny enough to provide much solar power. Seattle, for example, often has cloudy and rainy weather. Therefore, Seattle might find it difficult to depend on solar power. Currently, solar equipment is expensive, so the investment cost for solar power is higher than that of fossil fuels. In fact, solar power is the most expensive way to produce electricity today. However, prices for solar equipment are falling fast. In addition, solar technologies are becoming more efficient. This increased efficiency is making it possible to produce energy for less money. So let's look at figure 16. We can see here the sunlight distribution of within the United States. So this shows us solar radiation in kilowatt hours per square meter per day. And you can see the range of colors, which we have very little blue or purple on our map, except with the exception of Alaska. So it says sunlight in the United States. Notice that some locations receive more sunlight than others. Therefore, harnessing solar energy is more profitable in some areas than others. That makes sense, right? So if you get more sunlight, you can generate more solar or collect more solar radiation energy, and that means that you're being able to capture and store more energy, which means that you have more energy available to sell to someone else or to use yourself. So let's ponder this. Should people be forced to pay more for electricity in order to use renewable energy resources and reduce pollution? That's a good question, right? Because solar energy is so expensive to get into or to start up, a lot of people don't want to do it, but it does significantly reduce pollution. So should we force people or somehow incentivize them? And that's what the next question is asking. Should the government subsidize? So what does that mean? A government subsidy means that the government would give you some of the cost. They would pay you, or they would give you a discount in some way to make it more affordable for you to get solar power. So on number one, should we force people to pay more for electricity in order to use renewable energy resources and reduce pollution? I would say no. I don't think, based on our Constitution, that would be a good idea. You would get into a whole host of other issues. People not being able to afford it. You can afford a home, but you can't afford the pollution-free electricity. So then you have a home with no electricity. So then it's not considered basically inhabitable. So it's just it starts bringing up a lot of issues. If anything, it would be nice if you could get discounts or somehow we could make it cheaper so that it would just be an option people wanted to choose and they would be able to afford to choose. And if they can't afford to choose it, question 2 is saying maybe the government could basically give us a coupon for it. They would pay for part of it so that it would encourage or incentivize more people to opt to get solar power. And I would think that would be a good idea. But of course, the funds have to come from somewhere, so yet another issue. It's kind of a rock and a hard place sometimes moving forward on issues like this. All right, we're going to stop here for Monday's lecture. Go ahead and answer questions 1 through 6 in your workbook, and then we'll come back and continue on with chapter 18.3. All right, 18.3, we're going to be looking at harnessing wind power. Wind turbines are going to be the main thing of what we're actually looking at, but here is a image of a windmill. And indirectly, wind energy is a form of solar energy. The sun actually heats up the atmosphere, and the unequal heating of the air masses causes wind to blow. So people have used wind power for thousands of years. Windmills have been used to ground grain into flour, and they have been used to pump water, to drain wetlands, and to irrigate crops. And even today, farms and ranchers in parts of the U.S. still use windmills to draw up water, to give water to their cattle. But modern wind turbines don't look like the old windmills did. And we're not using it to perform tasks directly. We are using it to generate electricity. So let's take a look at the modern wind turbines. So recall that electricity is often generated using a turbine's rotating motor. So a wind turbine is a device that converts the wind's kinetic energy that's in motion, into electrical energy. And wind blowing into the turbine actually starts spinning the blades, and that is connected to a gearbox, as you can see in the lower image, the bottom image of your screen. And the gearbox connects to a generator, and that's where the electricity gets produced. So wind turbines are located on tops of towers, and some of these towers are taller than, a football field is long. Wind turbines are most often built in groups, and we call these groups of wind turbines wind farms. The world's largest wind farm contains hundreds of turbines. So offshore wind turbines, I want to mention, average wind speeds are approximately 20% greater over water than they are over land, which is our little did you know fact. And the reason for this, or for this and other reasons, offshore wind turbines are becoming more and more popular. Costs to erect and maintain wind turbines in water are higher than wind turbines that are located on land, because there's going to be more erosion and things like that. And they're being used, at a more intense rate. However, the stronger winds produce more power, which is the benefit, and that can make offshore wind turbines more profitable than the wind turbines that we would make on land. So even though it costs more, it makes more energy, so it makes more income. So the offset can actually be more beneficial. So let's take a look at some benefits and cost of wind power. We have a graph here that's showing us 5 nations account for about half of the world's wind power output. Like other forms of energy that we use, wind power has both benefits and costs, and some of these advantages and disadvantages we're going to be talking about in the next couple of slides. But first we're going to look at this pie chart, and its title is Percentage of World's Wind Power from Leading Nations, and here we have listed China, Spain, India, Germany, US, and the rest of the world is lumped together. And it's asking us to interpret the graph, and it wants to know what percentage of the world's wind power does Germany supply. So that's easy enough. We just go up, look at our pie chart, we find Germany, and underneath Germany we see that there is 19.8% of the world's wind power is coming from Germany. We can look at the other nations. The US is responsible for 20.9, at least as of the publication of the book. India was 7.9, Spain had 1.4, and China was only at 1% at the time. So let's take a look at this map wind patterns. The map shows how wind conditions compare in different parts of the United States. And we looked at yesterday a map that showed us solar radiation, right? But this one is looking at wind patterns. So over on the right, we see wind power density at 10 meters height. And this is measured in watts per meter. And we can see the different shades of blue, purple, and beige that kind of go over the U.S. So let's look at number 1. Interpret maps in general, which part of the United States and the eastern part or the western part has winds with the highest density. Oops, sorry guys. So it is, if we're looking at our color in our map, our beige color is going to be less wind power density, right? So less wind available, generating less wind power. That light blue, as we move to the center of the U.S. Or north on the East Coast, shows us an increase in wind power. And then the darker the color gets, the more wind power we are able to collect. So we would definitely say the left side of the United States is more color rich in the blues and purples, and so that would mean that they have the highest density. Number 2, find your state on the map. Do you think your state could obtain a lot of its energy from wind, and explain your answer? Well, ours is Florida, down in the southeastern portion of the U.S., so the bottom right side, and it is beige. So that falls in the 0 to 100 watts per meter, and so we are definitely not going to be able to, we have the least amount of wind power density. So we cannot reasonably get a lot of our energy from wind. Number 3, kind of ask us, because we were right in that southeastern part of the United States, do you think the southeastern part of the United States has many wind farms, and explain your answer? That goes along with number 2 that we just answered. No, there's not a high wind power density in the southeastern area. It's all covered in that beige color. So I wouldn't expect to see a bunch of wind farms, which means a high concentration of wind turbines. Number 4, on the basis of the circle graph in figure 19, what can you infer about the state of wind energy industry in the United States? So let's go back, and we're looking at just the primary nations that are producing wind power. And so independently, as of the named nations, we have the highest amount, and we're right kind of in line with Germany. So it looks like, I would say, yeah, we are well established. We're producing at least a fifth, if not nearly a quarter at this point, of the world's wind power. So if you want to jot those down and review those answers, you can take a look there, and we'll continue on with looking at the benefits of wind power. So like solar power, wind power does not cause pollution. So of course this is going to be its primary benefit, no pollution. The U.S. Environmental Protection Agency, or the EPA, has calculated that during a year, a 1 megawatt wind turbine prevents the release of more than 1,500 tons of carbon dioxide, or 6.5 tons of sulfur dioxide, 3.2 tons of nitrogen oxide, and 60 pounds of mercury. Under the best conditions, wind power appears to be highly efficient. One study found that wind turbines produce 23 times more energy than they use. Wind turbine development can range from 1 to 2 turbines to huge wind farms. Small-scale development can make local areas more self-sufficient, just as small-scale solar energy can. Startup costs of wind farms generally are higher than those of plants powered by fossil fuels, but wind farms are less expensive once they are up and running. But of course, that's part of the factor, right? The initial startup cost is part of the reason why we don't see more wind farms, even though they cost less once they are up and running. So what are the costs? We have no control over when the wind will occur, right? It's really unpredictable. And that's the major limitation, that it's unpredictable. And so that makes it not the most ideal electricity source, right? And some areas are windier than others. So it's not consistent. And wind power is definitely not a good choice in places that have little wind. So in that southeastern portion of the U.S. where we are, we're not going to get a lot of bang for our buck. The wind power industry has located much of its generating capacity in the states with high-speed winds, but these are often far from the large population centers that need the electricity. So the distance from the communities that need the electricity compared to where the wind is the most beneficial. Other factors besides unpredictability can prevent the use of wind power. For example, when wind farms are proposed near communities, the people living in the areas often oppose them. Many people think that the wind turbines clutter the landscape, so visually, or cause a lot of noise. In addition, birds and bats can be killed when they are flying near the rotating blades, or if they're set up on wind towers, they can fly into those as well. This is a negative effect scientists are not certain about how to handle. The best strategy may be to avoid constructing wind farms in certain places, such as along bird and bat migration routes. So definitely something to consider. All right, guys, that wraps up Tuesday's lecture, and it wraps up chapter 18.3. Go ahead and go in your workbook and answer questions 7 through 13 for classwork. Before we go, you can just take I thought this was a pretty cool image from the textbook of a guy sitting up on top of one of the wind turbines, and you can just get a sense of the enormous size. And I thought it was pretty cool. I thought it would be pretty scary to be this guy sitting up here. All right, if you would, you have homework tonight, and that is chapter 18.3. It is listed below. You can copy this over and email it to me, or just type up the answers and email it to me, or it is posted on Pearson Realize, so you can just go type it right into the website and submit it through there. If you are following along, I would like to give you a moment to be able to review some of those answers, and then go get that homework posted. All right, guys. I will see you Wednesday when we come back to finish up lesson 18.4 and the end of chapter 18. Bye.